So the second part is about the Inca and parameters. The parameters are contained in the .par file that I showed you before, and there are several types of parameters depending on what they control. So when I talked about the Inca model, I told you that the Inca model is solving several equations. So there are some equations that are reproducing processes in the soil. There are some other equations that are reproducing processes in the river reach. There are some other equations that are reproducing other things. So depending on what equations we want to, or what coefficients we want to modify, they can be found in different parts of the model. You modify or you check the parameters by clicking Edit Parameters. So in the menu you click Edit Parameters and you will display a drop-down menu with land phase, in-stream, reach, subcatchment and general parameters. So again, the land phase parameters refer to the soil processes. The in-stream parameters in this case are mainly the initial values of flow and water quality in the stream. The reach parameters refer to the in-channel processes, and the subcatchment parameters are other parameters that are also distributed into the catchment, and for example soils, etc., but are not really attributable to some specific land use. So they are in the subcatchment part. Let's go and see them. Let's start with land phase. Let's click on land phase. So you should display a little window with several tabs, 6 tabs on the top. Every tab is land use. So you have forest, grassland, wetland, improved grassland, arable land and urban land. So for each land use you have different parameters. Let's go, for example, to the forest tab, and in the forest tab you have other tabs or sub-tabs. The first sub-tab you should display is the processes sub-tab. In this windows, in this sub-tab, you should see some coefficients relative to, for example, denitrification rate, fixation rate, nitrification rate, mineralization, immobilization, etc. These are all processes that are happening in the soil. They are codified with equations and they have some coefficients. These coefficients have literature values, but since this is a conceptual model, we also need sometimes to modify them. In this case the model is already calibrated, so we don't need to modify them, but if we needed to modify the coefficients, this is the place.
Sorry, do you modify them manually or do you have like an optimization process in the model?
Inca doesn't have an optimization, embedded optimization algorithm, so you have to modify it manually. We obviously do optimization when we use this model, but we do it offline and with the command line version, not with the interface. But that would be really handy, actually, to have it in the interface. So other tabs are, for example, the initial values tab. We'll talk about later. We'll talk about the initial values later. The fertilizer tab. Fertilizer tab is where you write the fertilizer addition. For example, for the forest land use, we see that the fertilizer addition is all 0. So the fertilizer addition is codified by specifying a start day. So when the fertilizer, when the farmers start using the fertilizers, in this case it's 0 because it's not used. The fertilizer addition period, so how long the farmers use fertilizers. Nitrate addition rate, so how much nitrate they use as a fertilizer, and ammonium addition rate, so how much ammonium they use as fertilizer. You see it's all 0, but if you go to the arable tab, you will see that that is different. So the start day is 120, which is around April, end of April, beginning of May. The addition period is 108, so it's around between 3 and 4 months. the nitrogen addition rate is 1.2 kilograms of nitrogen per hectare per day, and the ammonium addition rate is 0.4. Then in the same subtab fertilizer we have another subtab apart from addition, which is plant growth, and here you define the parameters that define how plants, the plant development, the start day of the plant growth, the duration of the growth period, the uptake of nitrate and ammonium, etc., etc. This is important because not all the nitrogen that is actually that enters the soil, like by deposition or by fertilizers, goes to the water. Actually, farmers use fertilizer not because they want it to go to the river water. They want it to go to the plants. So the nitrate and ammonium uptake is defining exactly that, the amount of nitrogen that is taken by the plants and is not entering the water cycle.
Where did you get all these figures, Gianni?
All these figures, I usually start with literature values, and especially we have the Inca model has been used in so many catchments within the country and all over the world. So we have a lot of values that we know works and
so would you just take these from another Inca model that's
I start with
those,
and then I check the calibration and see if there are some problems. For example, with the fertilizer addition period and the growth period, sometimes, not always, but sometimes it's quite easy to see if it's okay or not, because you should see, for example, with the growth period, you should see a depletion in the nitrogen from arable lands during that period, and an increase right after that. So if you don't see that, or if the Inca results are like shifted compared to the observation, and maybe you will have to touch a little bit this parameter. Also because even if you have data about that, obviously not all the farmers will start using fertilizer the same day.
Yeah.
And it also depends on what kind of crops, and the growth period depends on the type of vegetation, so it's not just one value. This value is defined in an average figure, but it's not actually measurable. While what is measurable is a slightly different thing, which is the growth period of wheat and the start day of fertilizer use of farmer John or whatever. Okay, other tabs are, for example, the submodels tab. Here you have some coefficients that I usually do not change because they are quite the same everywhere in the country, like soil temperature, temperature response, and snowpack, which is not hugely important in this catchment, in the Salmonsbrook. Thresholds. In threshold we have the maximum soil moisture deficit, which is also not too important. Sustainable flow, you will see it's set to 9999, which means that it's a way to tell the model do not use this parameter, just disregard it. Process temperature, the same. And then we have the tab constant, which is actually quite important because we have the residence times. The residence times are parameters that describe the velocity of the water in different compartments. The direct runoff, the residence time, is the velocity of water in the surface of soils, in the surface, and the soil water residence time is the velocity of water within the soil. And we can modify all these parameters, and we will try to do that afterwards for different land uses. For example, I can modify the arable soil water residence time separately from the urban soil water residence time. But if you want to do that, you really need a lot of data. So you need, for example, a subcatchment where the arable land is very small, and the urban land is very small and the arable land is predominant. And another subcatchment where the arable land is small and the urban is predominant, and you need observation at the outlet of both subcatchments to check if the parameters that you are using are correct. So what we do normally when we don't have so much data, but we only have data at the catchment outlet, which is a mix of all the subcatchments, is to use the same parameter for all the land uses. And in order to help doing that, you have a checkbox which is called lock parameter set. It's in the upper part of the window. If you click that, then a red sentence will display, which is saying editing all landscape units. So if you have this checkbox checked, then if you change any of the parameters, we will change them for all the land uses, not just for the land use you're working on. Okay?
So is that realistic, Gemma? Because so the direct runoff residence time is the same for forest as it is for urban currently, isn't it?
The thing is, you would expect the residence time to be faster. For example, let's say the surface residence time to be faster for urban land than for forest land, and the same of soil probably, because in the urban land you have the surface is impervious, so that the water should flow more quickly. But the thing is, data is what value do I give to this parameter? I mean, how do I distinguish from the residence time in urban land and forest land without it being arbitrary? It would be totally arbitrary if I just change. For example, it's the direct runoff for urban land is set to 0.2. If I set it to 0.1 for urban land and 0.3 to forest land,
is there not research that exists
that would be
tell us?
Yes, but not exactly this parameter, because this parameter is not a measurable parameter, it's a conceptual parameter. So it's taking into account a lot of things, and among other things also the model error and the data error and a lot of errors. So it's very difficult to measure all those things. So if you change it like to 0.1 for urban and 0.3 for forest, that would be completely arbitrary. If you really want to do that properly, you would need an urban catchment and a forest catchment, both with records of flow. So you calibrate the parameter for forest land in one and for urban land in the other one, against records that are specific on those subcatchments and those land uses, and then you get a realistic calibrated values.